This is the presentation from Group 16. Today we are going to talk about the security of digital signature schemes. There are mainly 4 parts in our video. First, let's talk about the background. With the rapid development of digital hardware, there is an exponential growth of commercial applications involving banking and payment. Such applications increasingly demand more security and flexibility, which leads to the need for a new type of cryptography system to replace a written signature. Namely digital signature. A digital signature is a mathematical scheme for verifying the authenticity of digital messages or documents. A valid digital signature gives a recipient a very strong reason to believe that the message was created by a known sender, and that the message was not altered in transit. There are usually 3 parts in digital signature scheme: key generation, signing algorithm and signature verification algorithm. We are going to introduce 3 digital signature schemes: RSA, DSA and ECDSA. RSA is one of the first asymmetric key cryptosystems. It is widely used for secure data transmission. The encryption key is public and the decryption key is kept private. RSA involves 4 steps: key generation, key distribution, encryption, and decryption. Asymmetric key encryption involves 2 keys, public key and private key. Public key is used for encrypting the message, and private key is used for decrypting the message. Suppose that Bob wants to send information to Alice. If they decide to use RSA, Bob must know Alice's public key to encrypt the message, and Alice must use her private key to decrypt the message. To enable Bob to send his encrypted messages, Alice transmits her public key to Bob. Alice's private key is never distributed. After Bob obtains Alice's public key, he can send a message M to Alice. Public key is made up of 2 numbers called E and N. Choose 2 distinct prime numbers P and Q to compute N. The N equals P multiply Q. In order to calculate E, choose a random prime number that has a greatest common divisor of 1 with phi n. Now, Bob can use E to encrypt the message and then transmit ciphertext C to Alice. Alice can recover M from C by using her private key exponent D. The D is the multiplicative inverse of E with phi n. Given M, Alice can recover the original message M. The digital signature algorithm (DSA), based on the mathematical concept of modular exponentiation, and the discrete logarithm problem. DSA is a variant of the Schnorr and Elgamal signature schemes. It involves 4 operations: key generation, key distribution, signing and signature verification. The choice of algorithm parameters may be shared between different users of the system. A hash is an encoding that reduces the size of a message to a fixed bit length by using a specific encoding method. Then choose the key lengths L, module length N, and prime Q. After parameter selection, compute the hash function. To compute a single key pair for one user, Alice may sign a message hash function. Given a set of parameters, Alice's chooses an integer x randomly from 1 to q1. Then compute the public key y, x is the private key. The signer Alice should publish the public key y. That is, Alice should send the key to the receiver via a reliable, but not necessarily secret. And the signer should keep the private key x secret. Alice selects a random secret integer k from 1 to q-1. And she computes r and s. After that, Alice publishes her signature r and s. To verify the message, Bob performs the following steps. Download the public information. Compute w, u1, u2 and v. The signature is then only accepted if v equals r. The elliptic curve digital signature algorithm (ECDSA) is a variant of DSA, which makes advantage of elliptic curve cryptography. It is based on the difficulty of computing the elliptic curve discrete logarithm problem. Besides the key generation, the whole process of ECDSA is almost the same as the DSA. For the ECDSA key generation part, the inputs are G and N, where G is a base point of prime number on the curve. The Q equals to odd prime P, or a power of 2. The N is the order of point G. The output is public key Q and private key D. And the D is a randomly computed integer in the interval between 1 and n-1. The ECDSA signature generation takes D, G, and N as input, along with the hash function and message M. Then, select a random integer k, within 1 and n1. After that, follow the steps to compute the final signature values r and s. The signature verification part is to calculate the value V based on the known information, including the public key and signed message from the sender. To verify the signature, compare the V and R. The detailed steps are shown in the table. There are many applications that use digital signature technology. In practical applications, it will usually be too slow to sign the whole message. Additionally, there are also other security problems. In general, people only sign the digest of the original messages. In this section, we will give some typical application examples. The first common usage is SSL certification. For example, when we open a BBC website, how does it guarantee that the web page displayed in front of me must be generated by the BBC, and not being modified by others? It is achieved by a certificate that applied digital signatures. Users will download the public key to verify whether the content is signed by the website source. We open BBC homepage with Chrome browser. Click the small lock next to the address bar. And then click to view the SSL certificate. Here we can see the signature algorithm using SHA-256 with RSA encryption, which means that the digest is calculated by SHA-256 and signed with RSA. The certificate is the encapsulation of the public key, adding information such as the issuer and validity period on the basis of the public key. Another application is using a digital signature to initiate a secure channel network service, such as SSH. For example, some remote Git repositories on GitHub. A user first generate a key pair that fits SSH standard. Then he upload the public key to GitHub, and keep the private key secretly. When he performs any remote operation, the operation will be signed by the private key. And the remote server uses the public key to verify each operation's authenticity and integrity, which is efficient and safe. Bitcoin is a good example of ECDSA application. Each Bitcoin address is a cryptographic hash of an ECDSA public key. The ownership of the account is determined by who controls the ECDSA private key. If the account private key is lost, the owner will lose the money forever. Once the private key is stolen, the money in the account is completely owned by the hacker. Here we are going to see each algorithm's advantages and disadvantages. For RSA, we know it is the most commonly used algorithm. It is an algorithm can be used in both encryption and digital signature. It also provides acceptable performance. The DSA is similar to RSA in security. But it has some advantages such as a faster key generation and an easier achievement of key randomness. ECDSA is based on elliptic curve cryptography. Due to the characteristic of this algorithm, the key length can be much shorter compared to RSA or DSA. It means that signature generation and verification will be much faster as well. The disadvantage is that ECDSA is still not supported by some old system or low-version protocol. There are some common attacks on digital signatures to crack RSA or DSA key, such as brute force attack, common modules attack, low private or public key index. Moreover, cracking the hash function will be an executable way when faking the signature. There are also some kinds of perform attacks, including timing attack and power analysis attack. These attacks are usually applied in some specification scenarios. Our research report will focus on the security characteristics of each algorithm and provide detailed comparison and profound discussion. This is the end of our presentation. The sound source is synthesized by Google Cloud Text-to-Speech product. Thank you for listening.